Every long-period comet that falls toward the Sun arrives from roughly the same distance. Not from a random scattering of origins across interstellar space, but from a shell, a defined region between 2,000 and 200,000 astronomical units from our star. That consistency is the kind of pattern that demands an explanation, and in 1950, Dutch astronomer Jan Oort provided one. He proposed that a vast reservoir of icy bodies surrounds our solar system, continuously replenishing the comets we watch evaporate near the Sun. For decades, the default picture in most people's minds has been simple: a sparse, frozen wasteland at the edge of the Sun's gravity, occasionally flicking a snowball inward. That picture is almost certainly wrong. The Oort Cloud is not the empty void we imagined. It may be one of the most densely populated regions of the solar system by sheer object count. And understanding why changes how we see our place within the Sun's gravitational family. To understand the scale, consider where this structure begins. The Kuiper belt, that ring of icy objects beyond Neptune, extends to roughly 50 astronomical units from the Sun. One astronomical unit is the Earth-Sun distance, about 150 million kilometers. The inner boundary of the Oort Cloud starts more than 1,000 times farther out than the Kuiper belt. Its outer edge reaches approximately 200,000 astronomical units, which translates to about 3.2 light-years. That means the Oort Cloud stretches nearly to the halfway point between the Sun and the nearest neighboring star system. In volume, it dwarfs everything we typically call the solar system by many orders of magnitude. We are not talking about a thin boundary layer. We are talking about a structure so vast that the planetary region we know, from Mercury to Neptune, is a tiny dot at its center. What Jan Oort actually observed was not the cloud itself. No telescope has ever directly imaged an object in it. What he documented was a pattern in the orbital elements of long-period comets, those with orbital periods greater than 200 years. Their trajectories, traced backward, converged on a common origin distance. That statistical clustering was the evidence. The cloud's existence remains, to this day, a theoretical construct supported not by direct detection, but by the orbital fingerprints of the comets it releases. We infer the reservoir from what it sends us, the same way you might infer a mountain spring from the river it feeds downstream. Here is where expectation collides with what the models actually predict. For years, popular accounts described the Oort Cloud as a diffuse shell of widely spaced ice fragments, so thinly distributed that collisions between them would be essentially impossible. The reality supported by current modeling is considerably more populated. The cloud is theorized to contain billions of icy planetesimals, and that outer spherical shell is only part of the architecture. Interior to the spherical outer cloud lies a disc-shaped region roughly aligned with the plane of the solar system's ecliptic. This is known as the Hills Cloud, named after astronomer Jack Hills, and it is hypothesized to contain roughly 5 times as many cometary bodies as the outer Oort Cloud itself. Its outer boundary is estimated at around 20 to 30,000 astronomical units, with an inner border less well-defined, placed somewhere between 250 and 1,500 astronomical units from the Sun. If these estimates hold, the total population of icy bodies in the combined Oort structure is staggering. The Hills Cloud alone may dwarf its more famous outer counterpart by a factor of 5. The cloud is not empty. It is layered, structured, and immense. The mechanism by which we know this relies on gravitational inference and dynamical modeling. We observe long-period comets arriving in the inner solar system. We trace their orbits. We calculate what reservoir could sustain that infall rate over billions of years without being depleted. Oort's original insight was that comets are consumed by close solar approaches. They sublimate, fragment, and eventually vanish. Yet new ones keep arriving. Something must be replenishing the supply. The orbital statistics point to a source at the distances now associated with the cloud, and the required population must be enormous to maintain the observed infall over the age of the solar system. This is not a guess. It is a calculation constrained by the rate at which comets appear and the rate at which they are destroyed. But there are strict limits to what we can claim. No direct imaging of Oort Cloud objects exists with present technology. The bodies are too small, too dark, and far too distant for any current telescope to resolve. Our population estimates depend on dynamical models, which in turn depend on assumptions about cometary lifetimes, ejection rates during early solar system formation, and the gravitational perturbation history from passing stars and the galactic tide. Each of those inputs carries meaningful uncertainty. The 5-to-1 ratio of Hill's cloud objects to outer cloud objects is a hypothesis derived from modeling, not from a direct census. The leading explanation for how all this material ended up so far from the Sun traces back to the early solar system. Astronomers hypothesize that the material presently in the Oort Cloud originally formed much closer to the Sun, within the protoplanetary disk. The gravitational influence of the giant planets, particularly Jupiter and Saturn, scattered these icy planetesimals outward onto highly eccentric orbits. Over time, the gravitational torque of the Milky Way galaxy itself and the pulls of passing stars gradually circularized those orbits, trapping the material at enormous distances. This is not a fringe idea. It is the standard formation model, though the details of timing and efficiency remain actively studied. The cloud is, in a sense, the solar system's memory of its own violent youth, a record of everything the giant planets threw away. What makes the outer Oort cloud particularly interesting from a dynamical perspective is its vulnerability. It sits at the boundary of the Sun's gravitational dominion, defined by the Sun's Hill sphere relative to the galaxy. Objects there are only loosely bound. The gravitational pulls of passing stars, the overall tidal field of the Milky Way, and even the collective microgravity of the cloud's own constituents can dislodge material. This is not a stable vault. It is a region of constant, slow gravitational negotiation between the Sun and the galaxy. That ongoing interaction is what sends comets inward, and it means the cloud's population is not static. It has been shaped, depleted, and perhaps replenished by stellar encounters over 4.5 billion years. What could decisively test and refine our picture? A next-generation survey telescope capable of detecting extremely faint, slow-moving objects at distances of several hundred to a few thousand astronomical units could begin to directly sample the inner edge of the Hill's cloud. Alternatively, a spacecraft mission reaching several hundred astronomical units, far beyond the current positions of the Voyager probes, could perform in situ measurements of dust density and particle impacts that would constrain population models. Until such observations are made, the Oort cloud's demographics remain model-dependent. The structure is real in the sense that cometary orbits demand it, but its precise population, mass, and inner boundary await direct confirmation. What this changes is our sense of the solar system's true extent and composition. We live inside a structure that does not end at Pluto, does not end at the Kuiper belt, and does not thin to nothing beyond Neptune's influence. The Sun's gravitational family extends more than 3 light-years outward, and that space is not void. It is populated by billions of ancient frozen remnants of the same disk that built Earth. The Oort Cloud is not a footnote. It may contain the majority of individual objects in the solar system. We have not been looking at an empty margin. We have been failing to see how full it actually is, limited only by the instruments we have not yet built and the distances we have not yet crossed. The next time a long-period comet appears in our sky, consider its journey. It fell inward from a reservoir so vast it nearly touches another star's domain, released by a gravitational whisper from the galaxy itself. And it was not alone out there. It left behind billions,